All right, let's talk today about matrix diagonalization. First, we're going to introduce the concept of a similar matrix. So if A and B are n by n matrices, then we say A is similar to B, and also B is similar to A, if there's an invertible matrix P such that A is equal to PB P inverse. And we have this theorem which says if you have two matrices which are similar, then they have the same characteristic polynomial and hence the same eigenvalues with the same multiplicities. So remember, the characteristic polynomial is just the determinant of a minus lambda I. That's the polynomial that you get when you're trying to find the eigenvalues of a matrix. So this theorem tells us if you have two matrices that are similar, then they have the same characteristic polynomial, and therefore they're going to have the same eigenvalues. Okay, now why is this of interest? Well, think back to our section on Markov chains. We had this sort of equation that to get x1, we multiplied our transition matrix, which I'm calling A here, times the previous state vector. So for x1, A times x naught. A2 is A times x1, and so forth. X to the x sub k is A times x sub k minus 1. Now, we can, if we look at it like this, then to find, say, our state vector at time 10, then you need to find the state vector at time 9. And to find the one at time 9, you need the one at time 8, and so forth. And so to compute x sub 10, you need x1, x2, x3, up through x sub 9. Another way to look at it is like this, that we know, for instance, for x2, that's A times x1, but we know x1 is A times x naught. So we make that substitution, and so we end up with x2 is A squared times x naught. And similarly, x3 is A cubed times x naught. So in general, xk is A to the k times x naught. Now, unless A to the k is relatively easy to compute, this really doesn't help us. However, if A to the k is easy to compute, then we can compute x sub k much more quicker than going through and computing all these subsequent state vectors. Alright, so let's suppose that A is similar to a diagonal matrix. That is, A can be written as PD P inverse, where P is invertible and D is a diagonal matrix. Now, what does that get for you? Well, just look at what happens when you compute A squared. A squared is A times A, and when we substitute PD P inverse in for A, we have this. Now, the trick here is to group the P inverse times P together. Okay, so we got P inverse P right here in the middle. If we group that together, that's the identity matrix. And so then we get PD times the identity times D P inverse. And of course, anything times the identity is just that anything. And we got D times D, which gives us D squared. So A squared is PD squared P inverse. How about A cubed? A cubed is A squared times A. And so we take the A squared we computed up here, plug it in, times A, and do our trick again. Reassociate to get the P inverse P together. And we end up with PD cubed P inverse. So it looks like in general, A to the K is P times D to the K P inverse. Now, what good is that? Well, let's look at a diagonal matrix. Here's a simple 2 by 2 diagonal matrix. If we compute D squared, then notice that we end up with another diagonal matrix, and the entries on the diagonal are just the original diagonal entries raised to the second power. So in this case, we were computing D squared. So these are the original diagonal entries squared. D cubed, We get another diagonal matrix, and the entries are the original diagonal entries cubed. So just looking at this example, it appears that it's easy to compute powers of a diagonal matrix. We just raise each diagonal entry to whatever power we're trying to compute. So if A is similar to a diagonal matrix, computing powers of A is also easy. So we say that a square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. That is, if A is equal to PD P inverse for some invertible matrix P and some diagonal matrix D. Now, here is a very important theorem. It says an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So A is diagonalizable if it has n linearly independent eigenvectors. And furthermore, A equals PD P inverse with D a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. So this theorem not only tells us the condition, a condition under which A is diagonalizable, it also tells us how to compute P and D. Okay, P is a matrix that consists of n linearly independent eigenvectors of A. And continuing on, it says the diagonal entries of D are eigenvalues of A that correspond respectively to the eigenvectors in P. So P consists of the eigenvectors, D consists of the eigenvalues on the diagonal. So let's look at an example. Here's the matrix A. You can recognize this matrix. We looked at it in the video on the intro to eigenvalues and eigenvectors. Okay, so is it diagonalizable? Well, let's find the eigenvalues. So we take the determinant of A minus lambda I, and we end up with lambda minus 8 times lambda plus 2 as our characteristic polynomial. We set that equal to 0, and so our eigenvalues are lambda equals 8 and lambda equals negative 2. Now, at this point, we know that A is diagonalizable because A has two distinct eigenvalues. So it's a 2 by 2 matrix, it has two distinct eigenvalues. That means, since we know that distinct eigenvalues give us linearly independent eigenvectors, right? And eigenvectors that come from distinct eigenvalues are guaranteed to be linearly independent, and therefore A is diagonalizable. Now, to find P, we have to compute the eigenvectors. We already know what D is. D is a matrix, diagonal matrix with the eigenvalues on the diagonal. So take lambda equals 8, and we need to solve A minus 8 times I times x equals a 0 vector. And so we solve that system, and we end up with this vector in parametric vector form. So any multiple of 3, 1 is an eigenvector of A corresponding to lambda equals 8. So at this point we have one column of P. To get the other column, we look at the eigenvalue negative 2 and solve A minus negative 2I times x equals 0. And here's that. We end up with negative 1/3 1 as our eigenvector. So any multiple of that, any non-zero multiple of that would be an eigenvector. And so I multiplied by 3. Go back to that. I multiplied it by 3, and so end up with negative 1/3 for our second eigenvector. So the 3, 1 came from lambda equals 8. Negative 1/3 came from lambda equals negative 2. And so D consists of the eigenvalues, and the order that you put the eigenvectors into P is not important. However, once you establish an order, you have to hold that true for both P and D. So the eigenvector here, 3, 1, came from lambda equals 8, so we need the eigenvalue 8 in the first column of D. And then the eigenvector in the second column of P should correspond to the eigenvalue in the second column of D. Alright, and then if we want to just check our work, we multiply P, D, P inverse, and we end up with A. Alright, go through that computation, and you end up with A. So P, D, P inverse is equal to A. Let's look at another example. Here's another matrix, 3 by 3 in this case, and we want to know if it is diagonalizable. So, as before, we find its eigenvalues by looking at the determinant of A minus lambda I. We end up with this polynomial, negative lambda times lambda minus 2 squared equals 0. And the solutions will be lambda equals 0 and lambda equals 2. Now, lambda equals 0 occurs once, lambda equals 2 occurs twice since it's a squared term, so lambda equals 2 has multiplicity 2. It appears twice as an eigenvalue. Now at this point we know that A has only 2 distinct eigenvalues, so therefore we don't know if it has 3 linearly independent eigenvectors or not, so we don't know if A is diagonalizable or not. Just because it doesn't have 3 distinct eigenvalues doesn't mean that it's not diagonalizable. Okay, that theorem only goes one way. If it has n distinct eigenvalues, then it will be diagonalizable. If it doesn't have n distinct eigenvalues, you don't know whether it's diagonalizable or not. You have to actually see if you can compute n linearly independent eigenvectors. So in this case, that's what we've got to try. And actually for this particular problem, the real question is whether lambda equals 2, which occurred with multiplicity 2, will have 1 or 2 linearly independent eigenvectors. So let's look at lambda equals 2. We solve A minus 2i times x equals 0. And we end up with, notice in the matrix here, you can see that we've got 2 free variables, so therefore we're going to get 2 linearly independent eigenvectors from this eigenvalue. And so at this point, we've got 2 linearly independent eigenvectors from lambda equals 2. We know we'll get one more from the other eigenvalue. So at this point, we know that A is diagonalizable, and actually we're 2/3 of the way towards producing the P such that A equals P, D, P inverse. So we look at the other eigenvalue of 0 and solve A minus 0i times x equals 0. Then notice we got one free variable, so we end up with 1 linearly independent eigenvector. And so we know that A is diagonalizable. All right, here's our eigenvectors that we found. So we know that A is equal to P, D, P inverse, where P is this matrix. Now notice that the negative 1, 1, 1 came from lambda equals 0. So that means in the first column of D, I've got 0 here in the diagonal entry. These last 2 eigenvectors came from lambda equals 2. And so in the second column and the third column of D, I've got 2 on the diagonal. Now, before, in the 2 by 2 example, we actually checked our answer by computing P, D, P inverse. But for 3 by 3, it's not so simple to compute a inverse. And if you got a calculator, that's not that bad. But if you don't, then there's an easier way to check your answer. And that is to note that if A is equal to P, D, P inverse, if we multiply both sides of that equation by P on the right, then we end up with P inverse times p, which goes away, and then we end up on the left hand side with a times p. So AP would equal PD, and so we can compute both those matrices since only involves multiplication of matrices. You don't have to find any inverses. So you can check to see if AP is equal to PD. So if we compute both of those, you can see that in this case they are indeed the same, and so we can conclude that our P and D are correct. Alright, let's look at one more example. Here's another 3 by 3, and we want to know if it is diagonalizable. So we find the eigenvalues. I'm expanding about the first column here when I take the determinant, and end up with lambda minus 4 times lambda plus 2 squared. So again, I don't have 3 distinct eigenvalues. I only have 2. Lambda equals 4 occurs with multiplicity 1. Lambda equals negative 2 occurs with multiplicity 2. So we want to know, does lambda equal negative 2 have, are we going to get 2 linearly independent eigenvectors out of it? And when we solve a minus 2i times x equals 0, notice that we end up with this matrix in echelon form. And so we only have one free variable, right? X3 is free, and so we don't get 2 linearly independent eigenvectors out of this eigenvalue. And so we only get one. We're only going to get one linearly independent eigenvector from the other eigenvalue, from lambda equals 4. So that means we're only going to end up with 2 linearly independent eigenvectors, and that means that A is not diagonalizable in this case.